Let me start our session with a gray code and error detecting codes. In last class, we discussed that how to obtain a 4-bit binary, which is a binary coded non-weighted code is gray code. And in this session, we are going to convert your given binary number system into your equivalent gray code and gray code to binary. So in order to obtain your gray code for the given binary number, always we need to take your most significant bit of your binary number as it is that of your gray code most significant bit. So if you have a logical one on your most significant bit of your binary, that would be your gray code most significant bit, or else if you have 0, then 0 must be your most significant bit of your gray code bit. To obtain your second bit of your gray code, we need to perform an exclusive OR operation between your binary bits. So from your first bit to the second bit. Okay. So exclusive OR is nothing but a logical operation. So which can give you the logical 1 output if your inputs are 0, 1 or 1, 0. If it is having the same logical levels of 0, 0 or 1, 1. So then it would give you the output of logical 0. So now it means that if both the bits are different, so the result will be 1. If both the bits are similar, so then the result will be 0. So if both the bits are different, so your bit 1, your bit first bit is 1 and second bit is 0, your gray code bit will become 1. If your first bit is 0 or your second bit is 1, so gray code bit must be 1. If both bits are zeros or both bits are 1, you obtain your result bit is 0. So in order to get the third bit of the gray code, so we need to perform your exclusive OR operation between the second and third bit of binary number. And this process of your obtaining your next bit is continued till you get your last bit of your gray code. So fourth bit, if I require the fourth bit, then we have to perform your exclusive OR operation between the third bit and fourth bit. So now I'll explain this with an example. Now my given binary number is 01101. So from this given binary number, we need to obtain your gray code. Now exclusive OR logical symbol is a plus within a circle. So now I'm going to take your most significant bit as it is in your gray code. So as my given most significant bit of binary is 0, so that I consider it as my most significant bit of your gray code. Next, to obtain your next bit of your second bit of your gray code number, I need to perform the exclusive OR operation between the most significant and your second bit. So 0 exclusive OR of 1. So these two are different logical values. So hence we obtain your logical 1. Next, not to obtain your third bit, so we need to perform your exclusive OR operation between second bit and third bit. So here both are same quantities, logical ones. So hence we obtain your logical 0. Next, to obtain your fourth bit, perform your exclusive OR operation between your third and fourth bit of your binary. So now third and fourth bit of binary would give you 1 and exclusive OR of 0. So these two inputs are different logical levels. So hence we obtain your logical 1. To obtain the last bit of your gray code, perform your exclusive OR operation between your fourth bit and your fifth bit. So fourth bit is 0, fifth bit is 1. So 0 exclusive OR of 1. So both are different in logical levels. One is 0, the one is 1. So output last bit of your gray code is equal to 1. So this is the way of converting your given binary number into a gray code. Now how many number of binary bits are there? That many number of gray code bits are also available in your equivalent code of your gray. So there are given with the 5 bits. So hence in my gray code also I would have your total 5 bits only. Now let me do your given gray code to be converted into binary. So here also we follow the same one. So the most significant bit of your gray code is exactly equivalent to that of your binary equivalent. and then to obtain your second bit of your binary number, we need to perform the exclusive OR operation between your first bit of your binary with your second bit of your gray code. Then if these two are different, you obtain your logical 1. If those two are same, we would obtain your logical 0. So now here, now I'll explain this with an example. So this procedure of converting your equivalent binary is continued till you get your last bit. How many number of gray code bits are there in your given gray number? So that many bits are also available in your binary too. So now let I take an example of a gray number, which is gray code number, which is 01011. So this is your gray code, given gray code. Now we need to obtain from this gray code the equivalent binary. So most significant bit is 0, so hence I am taken as it is, that as considered as a most significant bit of your binary. Now we need to perform your exclusive OR operation between the binary bit of your most significant and the next bit of your gray code. So 0 exclusive OR of 1. So which are, these two are different. So one is 0, another one is logical 1. Then we obtain your second bit of your binary is 1. Now to obtain the third bit of your binary, so perform your exclusive OR operation between the second bit and your third bit of your gray code. So 1 exclusive OR of 0 is 1. So to obtain your fourth bit of your binary, so we need to perform your exclusive OR operation between third bit of binary and fourth bit of your gray code. So 1 exclusive OR of 1. So both are same in magnitude. So both are logical levels of 1. So hence we obtained a logical 0 is my fourth bit. Next, to obtain the fifth bit of a last bit of your binary number, perform the exclusive OR operation between 0 and 1. We obtain your logical 1. Since these two are different, so one is 0, another one is 1. So exclusive OR operation between the two different logical levels, we will get output of logical 1. So hence the equivalent binary equivalent of your given gray code 01011 is equal to 01101. So now one of the error detecting codes are also available here. So where we are going to, in this comes under your BCD codes only. So non-weighted, weighted, as well as your error detecting codes. So most familiar popular one is your parity bit method, which I am going to use as a error detecting code. So what is a parity bit method is, so we are going to use an extra bit, so that is appended to the code word of your given message or your given number, so which makes your number of ones in your given message either to odd number of ones or to the even number of ones. So here, based on the odd or even number of ones in your given messages, so those are classified into your given message is forwarded with your even parity or odd parity. There are two ways to represent your parity of even as well as your odd parity using your parity checker. So now a parity can detect your single bit errors, and sometimes it will also so detects your multiple bit errors too. Okay, so a parity bit is an extra bit that is included with your message, which makes your total number of ones either to even number of ones or to the odd number of ones. So if you prefer an even parity, then if the number of, and we said that it's a even parity, then the message should contain the even number of ones in your code word. So if you prefer a odd parity, then the number of ones in your given message should have your odd number of ones. Now I have a given message 1001001. So if I wanted to send this with an even parity, as this message is having 3 ones which are odd, if I add that extra bit and if it is 1, then only I could have this total number of ones are even. So then I can send from my sender to the receiver. So with the even parity. So if the message is I wanted to send this same message with an odd parity, this extra bit which I'm adding must be 0. So then only if I add this with a 0, so then only we have the total number of ones including the parity bit should contain the odd number of ones. So then we could say that, so this message was transferred with a odd parity. Next, how to check your parity at your receiver end. So total number of ones in your data, so which is of even or which is of odd. So for example, if I say that it is even, so now at your receiver end it will check for your received data bits of your data bits from your sender. So if it checks with your parity scheme, so then it recognizes that so there was no error is occurred. So if it is not checked, so if it counts your number of or receives your number of ones which are odd, so then it detects that error and it can ask for a retransmission of your data. Example, now I have a given number, so which is a message, so 10110000. Now if I wanted to send this with a even parity at my sender end, so I need to add an extra bit which is a parity bit. If I include that parity bit is a 1, then only I could have your total number of ones are 4 ones. So then I could say that, so my data bits are transferred with your even parity if I contain the total number of your bits along with the parity bit will be your actual message to be transferred from your sender end. So if it contain that even number of one, then we could say that it is transferred through a channel with a even parity. So now at your receiver, so we are going to check with the transferred message with the parity scheme, so even parity scheme. Now the receiver can check for the number of ones received. It will count how many number of ones are received in your given data, and it recognizes, so the sender has sent it, that message has sent the message, so through channel with a even parity. Now it counts for your number of ones which are received. So now it checks for your number of ones. If it receives the odd number of ones, it detects the error and asks for retransmission. Like this, it will check for your, and it is also happen for your odd number of ones too. So if the sender can send the message with the odd number of ones, the receiver has to check for the odd number of ones only. If it receives the even number of ones, then it asks for your retransmission of your data from your transmitter end. So like this, it can detect the error. So now the drawbacks of this is only here a single bit error is identified and we can't determine exact location of where the error is occurred. And the second limitation of this is, if it check for even parity or your odd parity, it checks your data. So for example, if the data is changed with multiple times, and even after changing the data, if it contains the even number of ones or the odd number of ones, it can't. First it will count your number of ones. If it receives with the 4 number of, for example, if it send it with your 4 ones, okay, and if you receive your 6 number of ones after your multiple changes, so it will count your number of ones only. So if it is matches with the even, so then it doesn't check for your retransmission. It doesn't ask for your retransmission from the transmitter end. The same goes for your odd too. So if your sender sends with a odd number of ones, with a 3 number of ones, when your receiver receives after multiple changes in the data through that channel, so when it receives the 5 number of ones, it will just check your count your number of ones received. If it is matches with that odd number of ones, it doesn't ask for retransmission. So these are the two limitations. Only single bit errors are detected here, but exact location we can't find it. And so if your multiple bit changes and if it's satisfied with the parity scheme at your receiver end, it is not asking for the retransmission. These are the two limitations of your even parity bit method, which is an error detection. So in order to avoid this, so we were preferring your error detecting and correcting codes, which are your Hamming codes. So that we will discuss in the next class.